All right. Excited to be here. If you can believe it, I've been doing this cybersecurity thing for a little bit of time. This is the first time I've ever been to SANS. So I'm goofy excited. I'm goofy all the time, but I'm goofy excited specifically today to be here with all of you. The second thing that really attracted me here is Hollywood, Halloween, HackFest, the whole thing. This is a really cool vibe. I know I'll be going to Universal Studios later, so I hope I'll get to meet a lot of you there. Just a really quick introduction of myself. Dave Weston, I lead operating system security at Microsoft. So I kind of have this weird job where I lead the defensive teams that are building all sorts of security infrastructure into the variety of operating systems that Microsoft ships and all these different products. So I have to work on everything from these tiny RTOSs in IoT that don't even have virtual memory. So everything Steve just said doesn't even apply to them. They're like DOS. To things like Xbox, play Call of Duty 6, it just came out. If it crashes, it's probably my fault. All the way up to Windows, obviously, various different versions of Linux, and of course, things like Azure Host. So that's a fun job, just building all of that infrastructure. But where it gets weird is I also lead all the penetration testing teams and red teams that focus on finding bugs. So a day in my life looks something like someone will come up to me and say, Dave, I just found the craziest 0-day you've ever seen in the crypto stack. And I'm like, yes, this is amazing. And then there's this awkward moment where I turn around and the person that wrote that's also on my team is looking very sad, and I've got to kind of broker this. So today, this is an offensive con, which I don't speak at a lot. I know there's a lot of penetration testers and offensive practitioners. So I'm going to try to give a flavor, but I'll definitely try to focus on folks here. So what I'm going to talk about is this AI thing. Heard of it? And when I thought about what I want to talk about here, I usually kind of wait till the last second. There's a lot of things floating around. I'm always working on a lot of what I think are interesting things and trying to figure out like what I would want to hear if I was in the audience today, particularly someone attending SANS who might do offensive practitioning as a day job, like Steve just mentioned. Like, what would I want to know in my world? And so there's obviously a lot of talk about AI. Most of that talk is really centered around what I would call an application level implementation of it. So exposure of LLM, maybe over services, maybe to a client app, maybe through a web app, right? So you're seeing things like prompt injection, poisoning attacks, et cetera. And that's all great and important. But there's this whole other side to AI that I think basically has not been talked about. And that's what it looks like to get on a device. Well, that's an infrastructure device traditionally, in a public cloud or somewhere running a heavy GPU like an H100. And what does a threat model look like there? And even increasingly, more of this is moving towards the edge on device. So we've seen just recently, and many of you have probably been excited, Apple just announced Apple Intelligence, which provides both some device side as well as cloud side integrations in a variety of different approaches to AI. You've got folks like Samsung, they're doing pretty wild stuff like these live translations. We're doing generative fill, and a lot of this is happening on devices. And of course, Windows 11 has this segment of PCs that we call Copilot PCs. It has a pretty heavy ASIC on board that can provide high performance math processing for basically doing really fast AI with great efficiency. All of this stuff is really not being talked about, and I think it's actually pretty interesting from a security perspective. So my goal today is to talk to you about what it's like to attack these things and also where we need to go from a defense standpoint. Again, Steve mentioned looking at browsers back in 2014. At this point, I think browsers are much easier than securing AI apps, so you're in for a ride today. And I'm really here to share, like this is hot off the presses, this is what I do every day. Some of this stuff is like a week old, so this is a very fast moving field, so I hope you'll enjoy some of this that we're talking about today. Okay, so why would you even want to do AI on the edge? You've got these giant public cloud clusters, and there's a lot of talk about GPU shortages. Many of you have seen like GPUs are being consumed at such a rate that people are actually building nuclear power sources specifically for data centers to do this. So again, a lot of the talk has been on the cloud integration side. But that's also why the edge is attractive. First, we have this new category of SoC that includes these on-device, high-performance coprocessors designed specifically to do the type of matrix math or tensor transformations that are intrinsic to AI, to modern AI. So Google has like their Pixel, which has this tensor chip, right? And they've had these ASICs for a long time available in their cloud. They're also on their devices. And what these NPUs do are basically provide very high compute in a very specialized way with really great efficiency. So that does two things. One, it cuts the cost of building these cloud-based applications that are incredibly expensive from a compute and electricity, data storage standpoint. It also does things like reduce latency. So depending on where you are, you want to use AI. Maybe you're using it in a manufacturing capacity. I work with a lot of manufacturers who will do things like computer vision on specialized oil drills, and the model will basically say, oh, the tip of that machine looks like it's about to break. I want to swap it out now. Right? These are very specific applications that are critical path, and having latency to the cloud to do that is incredibly expensive for them, right? And it could be challenging. There may be no network available at all. And then finally, this is probably something familiar to you all, which is AI can collect a lot of data. Sometimes that's very private or sensitive data. I'm sure many of you would like to stay in control of that data, and there's no better way to stay in control of that data than to keep it local. And particularly in places where there's maybe sovereign requirements, there might be data laws, having the information on the device might enable scenarios that folks might not be otherwise comfortable with sending to the cloud. So these are really three good reasons to say, at this point, every major device coming out, whether it's a Mac, a PC, an Android phone, an iPhone, all have some kind of accelerator. So the question of the day is, what is this being used for, and what are the security implications? So again, as I mentioned, the NPU basically operates on, in most cases, a fundamental math primitive that you can think of as a matrix or a tensor. And that NPU is going to be on SoC right next to the GPU, which is going to focus on graphics, as well as the CPU. So there are a variety of different hardware attacks that might be available to you if the SoC is not designed correctly. There are also various interesting ways in which those can be accessed through the application stack. So just talking about Windows, and of course, a lot of this transfers over to Apple, as well as Google and Android apps, which have a very similar stack. You essentially have a set of higher level constructs for writing AI-enabled applications. So that could be things like doing computer vision and object extraction, like there's a dog in this photo. Doing things like video processing, you can extract text. All of those basic primitives will exist in these APIs, and that in most cases will be exposed both from web-based bound APIs to JS, as well as C++. Then underneath that, depending on the library you choose, there'll be a variety of runtimes. And these, you can think of these like application stacks. So a very common one is PyTorch, which is actually developed by Meta. There's also TensorFlow, which is developed by Google. And these are basically Python or other language runtimes that wrap more sophisticated hardware constructs, like CUDA from NVIDIA. You've got ROCm from AMD, and these are different application stacks that people choose. One of the things that Microsoft has that's kind of interesting is something called Onyx, and that's the sort of write once, run anywhere, where it does meta translation to all these different runtimes. On the Windows stack, then this is then translated into what we call DirectML. If you see the terminology direct, that's because what else does really high performance matrix-based math? GPU and game development. So our Direct 3D team actually translated much of their skills into what's called DirectML, and it works very similar to shader math. So shader, pixel shaders, and vertex shaders are something that have been around a long time and have a lot of applications here. So you write this upper level application, it's converted into DirectML, it's submitted to the GPU or NPU, and that buffer is then returned, which is usually a blob of pixels or some other construct, and that is how these applications are built. This is where things get interesting from a security standpoint. So the on-device AI threat model is quite interesting. Most of the discussion that I've seen in the public is really around what I would call more IP or DRM. Things like you can leak the model weights, which is a very viable sort of DRM concern, right? Some of these companies, for example, OpenAI, have billion parameter models that if those weights were leaked, they might lose millions or billions of dollars in IP. And if you're going to push these out to devices where physical attacks are in play, where the user is administrator, et cetera, you end up having in some ways to put even the administrator of the device outside of the threat model. At this point in time, they're really the only consumer devices that have been capable of doing that traditionally are really locked down mobile devices like iPhone, et cetera, or really locked down gaming devices like a PlayStation or Xbox. Those are designed to say the user can't hack them. So we have this fundamental problem here of if these models get out and get leaked, even one time, there's a big IP issue. But that also transfers over into security. So obviously, leaking the weights is interesting from an IP perspective, but as these models become critical path into security decisions, modifying them or tampering with the weights can actually have security consequences. Think about facial recognition models, video security models, where modifications of those weights in one direction or another can actually lead to some real-world security implications. The other thing that I find fascinating is even more than the models, what we see in practice is that the biggest risk for on-device AI is because of the computational power, there's a necessity to collect more sensitive data. Again, on-device gives you privacy, so it can be an enabler for use cases like processing screenshots, taking more photographs and doing imagery there, doing text extractions from photos that are in your photo library. And that requires data to do both training and inference. So what we see is a correlation between the more computing power you have, the more, and especially if it's on device, the more likely you are to store data on that device. So a few years ago, really the largest data caches would have been what? A SQL server, a database server, a file server. Now when you have single terabyte phones or laptops, and you have a collection of sensitive data to be processed, these become really interesting targets from a security standpoint. So they become exfil targets. And then finally, really the abuse of any of these APIs. Everything in this world is dual use. So if it's useful for positive processes, it can also be used in post-compromise tradecraft. So let's talk a little bit about what that looks like. If you haven't seen this, I really have to recommend a talk from CCC in 2023 from Boris Larkin and the other team at Kaspersky, who looked at a full-chain iPhone exploit called triangulation. And this quote is very ominous and accurate from Boris Larkin, who is a very accomplished malware researcher. He said, based on his analysis of the triangulation chain, in the future, malware will just have to ask AI what it knows about you. We should prepare for that. And that might sound like sci-fi until you get into this talk and you see that this is actually more reality than it is science fiction. A great example, probably the best example we have where post-compromise tradecraft is aided by AI was this operation triangulation. So again, it was a full-chain exploit, ostensibly targeted at Kaspersky researchers. One of the things that this full-chain exploit did is it got access to these phones. And ostensibly, there's a bunch of interesting things on these phones to exfil, but as I mentioned previously, phones at this point are what, minimum 256 gig NVMe, all the way up. My phone's a terabyte because I keep everything local. And so just sorting through that and then exfilling it has become an incredibly complicated computational task. I know many of you are familiar with all sorts of these different tradecraft tools, C2 tools, your Cobalt Strikes, et cetera. Last I know, Cobalt Strike can't search through a terabyte of data very quickly and index things based on tags. But guess what can? iOS Spotlight. Have you ever noticed what Spotlight can do? You can type in a search. It looks through all your iMessages. You can type in dog, and all of a sudden your photos are returned. Have you ever thought about what it might mean if someone could get access to that? That is the reality of AI and accelerated kind of processors in action is Spotlight. Now think about what it means for attackers to get that Spotlight level capability. So what we saw in triangulation is, again, once you get to this significant privilege level on the iPhone, it was pretty trivial for these attackers to search through photos. They weren't just looking at photos, right? They weren't interested in pictures of Kaspersky researchers' dogs. They were looking for things like documents. So again, there's a very powerful OpenCL-based classification API that allow you to say things like, show me all documents in this photo library. Show me all documents that contain foo or bar. And that enables an attacker who might have otherwise spent months trying to keep persistence on a phone, which is very difficult, right? We're in an age where everyone's supposed to reboot their phones every week, to being able to get to what they care about very quickly. So one of the predictions I have in very short order, your Cobalt Strikes, your interpreters, all of your sort of post-compromise tradecraft will be enlightened with this type of search indexing. It's just too powerful. And so I think this gives us an idea of what it can mean when AI is attacked and what the threat is there. The second area I want to show you is a much more concrete example of what I call model tampering. So again, this device here, when I ran upstairs, I ran up here and decided to present, I used my face to log into the phone. That's something we call Windows Hello. This has been around for a very long time. And what Windows Hello will allow you to do is uh, basically do facial recognition for fingerprints or face. And all of that matching traditionally is actually done in software at admin. So if you got, or sorry, in software in normal world. So an admin level attacker can do things like modify the model matching code, can modify the templates and the feature extractions, can get access to the data that's used for inference and training and improvement. Basically, the admin has access to all this information. The challenge with that is that's been okay when we use facial recognition for only remote authorization. Originally, when Hello was designed, it was designed primarily for doing things like facial recognition or bio to log into a website or to log into your computer. That is really a remote threat model, right? It assumes that all of the threats are off device. The game changes significantly when the threats become on device. In this world, Hello is not hardened to that. So this is a great example of, again, AI being used in the critical path for a security decision. If you modify this template or this database, you now have authorization or access to whatever that particular bio is set up for. So as runtime authorization becomes more critical, we have to change the threat model. So for example, one of the features we just announced is all of your Windows machines will no longer run an admin by default. You'll have to use face or fingerprint to elevate just in time to do operations, essentially fancy sudo. On Mac OS and iOS, it's been that way for some time with system integrity protection or SIP, where you'll get a facial or fingerprint prompt to do runtime authorization. That becomes challenging, right, when there's access to some of these features or ability to do modifications or attacks against them. So to fix this, we had to actually redesign the entire biometric framework here and the way all of the models work. So we did that in true Microsoft fashion by putting all of the feature matching into a virtualization-based security enclave or a VM. So we moved all of the code, data, model training, and all peripheral access out of the normal world into this VM. And this is essentially so that even an administrative attacker can no longer get access to this feature database or any of the code to modify it. This is absolutely crucial if you're going to do runtime authorization with bio. You've got to make that happen. Arguably, the most interesting part of this is that all of the fingerprint devices, so for example, the fingerprint here and the face device, actually never traverse standard windows. We use a hardware construct called an IOMMU, or Input-Output Memory Management Unit, that carves off all DMA and PCIe paths between the peripherals, so the fingerprint or face, directly into a virtual machine that does that mapping. So that means not only can an attacker not modify memory across that boundary, but they also can't sniff or otherwise cause modification or changes to any of the peripherals doing the bio matching. So this is a good example of AI in practice, right? You wouldn't think like of AI in the traditional sense of facial recognition, et cetera, but those are actually probably the most widely spread use of AI on device, and a good example of where threat model is going to change for these things. Another good example, or another good area to think about, is what I was calling these data threats or data attacks. So again, AI, super useful for operating on large-scale data, especially using common human language. So I don't think you would love traditional search today, right? Windows has this search indexer that mostly uses regular expressions and a few parsers to get things going. You can imagine that doesn't find things as well as what you would get today on modern photo editors, where you can say, give me a picture of my dog in a red shirt, and it returns back immediately. However, all of that requires you to have data to feed into those algorithms. And again, there's this push towards collecting more of that. And so this, as I said, there's a symbiotic relationship between the more AI power you have, the more data that's there, and the more threats there are against it. So one of the, I think, biggest challenges I've seen personally is that as the data gets more sensitive, customers get less and less comfortable with the security boundaries they have today. So for example, on a Windows machine, if you're at administrative level, most of the security of the system is already bypassed. I think all of you know that. You can dump credentials, load drivers, et cetera. We say, like, that's not a security boundary. It's no longer a vulnerability. It's just abuse. Over time, we've introduced new constructs like virtualization-based security, TPMs, and other things where even the admin can't get access to them. But those things are very limited in scope. And generally, the more you put into those, you get diminishing returns in security. So if you put everything into this second virtualization-based security enclave, you really haven't achieved much. You just shifted the attack surface. So there's ended up, I think, being two strategies for protecting this kind of data, and particularly the keys and API access to this data. The first is what I would call forward security or forward security layers. So why are you comfortable using Spotlight on your iPhone? It's not that Spotlight is processing in a separate enclave or anything like that. Why you're comfortable with that is you have code integrity, you have exploit mitigations, you have mandatory access control, you have principle of least privilege. You have all these different layers of security that say it's very unlikely, right, millions of dollar exploits we're talking about, for you to get to access to this data. And it's very similar on Android. So the reason you can do Pixel 9 screenshots and do processing, et cetera, is because there's a lot of confidence in those forward layers of security. So any kind of access means the device is already gone, which is hard to do. On desktop machines, and I'll include Mac OS, Linux, or Windows, that's not so much the case. Most of these desktop systems are fairly open. Even Mac OS, you can still bypass gatekeeper, right, with the right key combination, et cetera. And so there is not a guarantee of all these layers. But yet these systems need to have AI as well. So what ends up happening is to protect these increasing data caches and their keys, et cetera, you need to create additional security boundaries that don't just mean locking the machine down more. Now, locking the machine down is great, but at some point, the whole reason people use Windows or Linux is because they can do what they want to do in a bunch of variety of scenarios. So you can't lock it down the same way you could an iPhone or an Xbox. And this is kind of the challenge from a defender standpoint. So Windows Recall, I think, is a great example of this. For those of you who don't know, what Windows Recall does is basically uses the NPU and screenshotting to create a modern search experience. So basically, you configure which applications you don't want in this system. You configure how long to store data. It takes screenshots of your machine. It does object recognition on those and does text extraction and then creates a database. So it's very useful because you can say things like, show me Teams when someone was wearing a black shirt with pink writing from 30 days ago. It'll take you right to Teams and the Teams recording on that. So incredibly powerful, very similar to Spotlight in a way on desktop. But also you can imagine storing screenshot data and having that accessible, even if you get compromised, is not a great feeling, right? So what we heard clearly from consumers is like, hey, Microsoft, I know this is hard, but if you're going to have a feature like this, I want to make sure, even if I get hacked completely, that that data is not accessible. And for an operating system person, that's like a mind explosion. Like, what do you mean? Like, you want me to do something more than after you get root protecting? The answer is yes. And of course, we've done that in the past with things like, NTLM hashes, et cetera, but nothing like this. And so Windows Recall has been a really challenging architecture to land. I think we've landed it, but there's a lot of lessons learned, and it's got to be much simpler to do this if AI is going to get secure at scale. So the way we approached Windows Recall is with a few core principles and properties. First, we need to encrypt all important data elements, but here's the really important point. Not all encryption is created equal. All of you have probably heard of an API called like DP API. That's Data Protection API. It's a great API, allows you to encrypt stuff, but all the keys are stored in registry, which means the administrator can get access to those keys. You can use things like EFS, Extended File System, or Encrypted File Systems. EFS, also keys stored in registry. So not only do we have to encrypt things, but we had to make sure that the keys were protected against the administrators and that the code that operated on those keys is also protected. The second thing we wanted to do is make sure everything was isolated that was part of this. The third thing, and this is really important, if we're going to assume that this data is so sensitive, we have to protect the administrator from themselves, we have to get into a property that we call proof of presence. Proof of presence is pretty simple. You want to make sure that not only is someone authorizing or authenticating with multiple factors, but also that there's some sort of presence detection. A good example of this is the YubiKey. Why do you have to tap a YubiKey? That's just showing, hey, a human's here. Like someone's here asking for this. It's not just that there's a multi-factor thing inserted in the machine. They didn't walk away and go to the bathroom. They're actually present at the moment. You can also do that with fingerprints or face. So what we wanted to make sure is if someone was going to turn on Windows Recall, that they were intentional about that and that the user who owns that machine, at least from a login perspective, is also the person saying, I want this and I want it enabled. We call that concept proof of presence. We also wanted to have runtime authorization. So not only present when you configure it, but each time you go and touch this sensitive data cache, we want to make sure that, hey, you're there, you want to do this, and then you have a timeout around that. Now finally, here's a really complicated and interesting rub. So cool, you've got everything isolated, you've got this runtime authorization, et cetera. All of you know this, all of you are pen testers. As an attacker, I can still just chill, wait for the user to do an authorization on accessing Windows Recall data, and then either inject my code or just intercept the data that's in memory back to the application at the time that happens. So we have to protect this as well, which is tricky. So what did we come up with? Well, we came up with what I'd like to call, at least that I'm aware of, the most secure Windows app I'm aware of. And I run Windows security, I've been doing this a long time, so I feel pretty safe saying this. And I'll talk to you about how we mitigate this. First, every time we take a snapshot, we encrypt it with a public-private key pair where the private key is only stored in the TPM. So as soon as you take a screenshot, it's encrypted. And all of that information, including all of keys and all processing that data, is done in a tiny VM that we call an enclave. The second thing that happens is just to set up the feature. Again, you have to use Windows Hello and say, I'm here and I'm the user, like I want this thing. If you want to change any of the privacy settings, if you want to change the amount of time stored, each time proof of presence is required. We use that secure version of Windows Hello where all of the biometric data is piped directly into this second segmented isolated context. So your private key pair is tied to your face or your fingerprint being recognized. That asks the TPM to release the private key, which allows data to be decrypted and sent out. When the API endpoint is accessed between the standard operating system and the enclave, you have to do a runtime authorization. That has a standard timeout of 15 minutes, not too dissimilar to say like 1Password or LastPass, et cetera. Even then, those applications are all PPL'd, protected processes, just like Defender. So these are normal world applications that are temporal, but they're still protected processes even against administrators. You need a kernel driver, et cetera. And even then, if you get access to that API endpoint, we have implemented anti-hammering. So think of Cloudflare for IPC. So if you hit it too many times, we don't put a CAPTCHA up, but we just say, you've hit it too many times, and we're not going to let you slurp out the data. That's how we stop someone from just injecting code into this client and then saying, star.star, send me everything, because that would allow you to exfil all of this data. So these 4 constructs are in place just for this singular application. So this required a lot of coordination, it required a lot of expertise, it required a lot of stuff that's never been done before to be done. And again, we're not really protecting the AI here, right? What we're protecting is this massive data cache that's concerning for users. So we need a better way to do this. So learning from recall, how do we make this more generalizable and increase security? That is the question. So the challenge for defenders in a situation of building an AI application like this are numerous. The first is, regardless of the segmentation between this trusted world and this normal world using enclaves, et cetera, you still have a bunch of constructs that the administrator, and if they're an evil administrator, still has access to. That includes things like loading kernel drivers, drawing onto the screen, changing pixels. There's only so far you can go with trying to segment those 2 worlds before you just get into this sort of blurry mess. The second piece is like, this took the best people I have, the best pen testers, the best everything, and there are still things we would like to do better. There are still open challenges. I think we want to get into a world where your next great app developer, someone coming out of college or high school, can do this securely. We've got a long way to go. The NPU and GPU acceleration are currently not available from trusted execution environments. That means you cannot talk to the NPU directly from, say, an enclave. And so that requires a lot of coordination, a lot of PKI that's challenging. And then finally, here's the rub. all of this information is being done, all of this processing is being done in a separate enclave, customers may still be suspicious of Microsoft, Apple, or Google and not fully trust them. How do I know that someone didn't sneak in a back door? The more private the data becomes, the more the demand or the bar increases for making sure that that data is secure. So all of these are open problems we need a good solution for. Enter what we call confidential VMs. So confidential VMs were invented for the public cloud and are available currently on server CPUs. And what confidential VMs were designed for is to mitigate the issue of an insider threat at a public cloud. As people have migrated to the cloud, as companies have migrated to the cloud, they naturally have to sort of intrinsically trust the staff at those clouds, at AWS, at Google, at Azure. And not every customer wanted to do that. Maybe they do banking transactions. Maybe they're mining for Bitcoins and they don't, there's a lot of money involved. They don't want, somebody who's just walking through the data center to have access to that, or even a Microsoft employee that's corrupted. And so confidential VMs seek to take the fundamental execution or compute unit of the VM and say that even though this VM runs on the host, the administrators and the host operating system have no access to it. That's mind-blowing. The way that is done is through encryption of DRAM and segmentation through the hypervisor. And all of the encryption of that DRAM is based on customer-controlled keys that the customer controls policies on. So the customers can do things like say, I want my VM to run, but only if the VM and host operating system have software that matches these SHA-256 hashes. Only then is my derivative key released from my HSM. Microsoft can never interrupt it. It's being shared directly to an AMD, Intel, or ARM CPU. And all of the decryption for compute is done in DRAM segments that even a Microsoft root administrator on this Windows system cannot use. So each confidential VM is fully encrypted. All the encryption keys are in these dedicated hardware registers. And another way of saying that is even a compromised software change from Microsoft cannot lead to data leakage. Only a compromise of, say, AMD or the HSM, et cetera, or Intel, one of the hardware vendors. So we're removing Microsoft from what we call the TCB, or the trusted computing base. So this is a super cool construct, but it's also crazy in a lot of ways. For the history of computing, we've always had this concept of isolation from what we call the inside out. So if you build a sandboxed app, you're protecting the operating system from the app being compromised. We're inverting that. We're saying if the host is compromised, we don't want you to be able to look at our compute. So from an attacker standpoint, this is like crazy. We're going to change the entire threat model, which means there's all new bug classes and all sorts of interesting attack surface. So how does this all work? It's fairly complicated, but I'll give you the gist of it. Basically, all of the components on both the host operating system as well as the confidential VM are measured by hardware that's outside of the control of the hypervisor vendor. That's exposed through secure hardware registers and segmented at the hardware level into these registers that only the client VM can look at. Those can be set off-box securely with attestation and ledger APIs. And that means every piece of software, not just like the boot mechanisms, but the kernel, et cetera, can be independently verified by a customer, and they can decide what that policy is before key release exists. This is actually, I'm going to go a little far. This is the coolest application of blockchain I've ever seen, which is the confidential software ledgers will actually give you an immutable hash of known software that's been vetted by security researchers, et cetera. And so you can start to say, only these hashes are the ones I want because I know they've gone through like independent verification, et cetera. The second thing that's involved here is what we call a paravisor. Why are we calling it a paravisor instead of hypervisor? More of the work is actually done now on the CPU core than in the software. So it's a very light layer. We actually call it the HCL, or the hardware compatibility layer. Why? The more hypervisor code written by Microsoft, the more you have to trust Microsoft. The more hypervisor code written by Amazon, the more you have to trust Amazon. And the whole point here is I want to remove the trust of the public computing provider. And then finally, all these identity and measurement constructs are done in code, so you can do independent verification and reasoning about them. So here's what the threat model looks like from AMD. And by the way, I applaud AMD for their SEV SNMP, which is their highest level of confidential compute. Also, Intel has something called TDX, or Trusted Domain Extensions, and ARM has that. But I think AMD did an awesome job of explaining what they mitigate and what they don't. I really want to see this kind of like food label on every piece of hardware I buy, but this is awesome. So I'll just give you a second to look through this, but there's a couple of interesting things that they're very clear about. One is we can't stop guests, right, from doing DOS, or we can't stop the host from denial of service on the guest, rather, because they still have access to all the hardware constructs. We can't stop things like active DRAM corruption, which are doing things like fault injection, right, through like voltage glitching attacks, et cetera. So they're very, very clear about what they can and can't do. So in a nutshell, what they're saying is we mitigate everything except the host getting compromised to DOS your VM, or someone coming up to the machine with an FPGA to do voltage attacks. So that's pretty cool. Obviously, there's a lot of dependencies here on their PSP processor and many other systems. But in a nutshell, they claim to achieve this. So the next question you have is, this is pretty cool. This gives us essentially a generalized VM environment that we can run on these systems. That would be pretty cool for AI, right? Because rather than doing this open heart surgery that I had to do on something like recall, someone who's doing an AI application on sensitive data could basically maybe just set up a lightweight VM. It could be confidential, so even if an administrator is compromised, everything that's happening from that AI perspective is generalizable and fully protected from everything but hardware glitching and DOS. Sounds pretty awesome, right? This is something that's available today in Azure, AWS, Google Cloud. But how do we bring it to the client where there now is sensitive AI processes? Well, the answer is it's not available today, yet. Most of these vendors all have it in their roadmap, but there's something we can do that's pretty close. We can get almost everything I just said modulus distrusting Microsoft now by doing something that we call a software CVM or a virtualization-based CVM. Hardware CVMs, right, in hardware have things like DRAM encryption, management of keys directly in hardware register, para-virtualization, et cetera. And that's all great if you don't trust your vendor, which again makes sense in the public cloud where anyone can make a code change to get access to your data. You may also want that in the client, but by just taking a hypervisor and making it the unit of trust, we can reduce our trust down from anything the administrator can touch to 10,000 lines of hypervisor code. So Hyper-V that runs VBS is roughly at its core about 10,000 lines of code. And so if we can get it to manage the keys, an attacker could still potentially compromise a VM, but they'd have to find a pretty sophisticated vulnerability to that. To give you an example, we pay out about $250,000 for a hypervisor bounty. A kernel EOP is roughly $15,000. So more than 10x in terms of payout, probably a lot more than 10x in terms of security difficulty. So this virtualization-based CVM has the property of being generalizable across all these systems today. So that becomes a really interesting option for doing AI. Again, remember, we want you to just be able to take your application, write it once, no specialized knowledge, slap it on a machine and say even the administrator can't compromise that. That's also super useful for other things. Anti-cheat, right? I don't know how many of you have played video games much, but the biggest problem there is that you can't trust the user not to hack their own game to cheat in online games. That's another place where this is potentially a very interesting application in technology. So now here's the big problem. This is all well and good, right? You've given us a generalized compute that is protected even from administrative modification. What's the problem with that? Well, you have all peanut butter and no jelly in this sandwich. To do AI, you need not just generalized protected compute, you need generalized protected compute on a GPU or an NPU. So now we've just taken the circle of trust from the CPU to the NPU. Azure's done this for some time. We actually introduced about a year ago on NVIDIA's A100, now the H100 has superseded that, the ability to do confidential compute directly on a GPU. How does that work? Well, first, NVIDIA has a construct that's pretty similar to what you see on Intel and AMD CPUs, but just for the GPU. So a concept of para-virtualization, you can take one H100 GPU, which is like worth its weight in gold or platinum or whatever the precious diamonds, whatever precious stone you want to think of, and they subdivide it into multiple accesses from VMs. Now, each of those VMs is para-virtualized, but you want to make sure that the host itself cannot modify any of the video RAM, change any of the PCIe or DMA channels to get access to what's being submitted there in terms of like AI workloads. And so what you do next is you set up a secure channel between a confidential VM and a confidential para-virtualized GPU. And to do that, you want to do a set of key exchanges over PCIe that's known secure. There's an open protocol for that called SPDM. So you do this key exchange. And for those of you who don't know, PCIe, right, which is fundamental GPU, is actually a packet technology. So you can do sort of like almost IP style packet technology over PCIe. You can almost use a style of TLS for this. And so we're now able to say we have attestation, we have a ledger to verify software, microcode, GPU, CPU. We can do remote attestation. I control keys. And I now have the entire chain that I need here, which is pretty dope. So now that I have all that set up, I can take my AI workload, containerize it or create a VM, and that's immediately now going to have access to GPU, so I can do all of this computation, et cetera. So doing things like screenshot processing, AI modeling, image extraction, all of that stuff is secure all the way up to basically hardware glitching. So even like memory forensics dumps are going to be fully encrypted in DRAM, et cetera. So you have a pretty strong threat model here. You can generalize this even further. So again, this is for on-device, but you can also do this for models in the cloud. So for example, on Azure, if you wanted to take OpenAI and then train some sort of sub-optimized model for that, you can do that all on confidential CPU and GPU, which means even the data coming off device and going into the public cloud is declared confidential. So this is pretty cool. This allows us to do on-device processing as necessary, but when we run out of compute power, we have a bigger workload, we don't lose any privacy or security, we stream that to the cloud. So obviously, there's a lot of components that are involved here. There's a lot of interesting attack surface, one of the reasons I'm bringing it to this group. But in concept, we have all the primitives we need to do this. One of the primitives I want to continue to point out, because it's super critical, is this concept of the transparency ledger. The transparency ledger exists because there's going to be software loaded in these VMs that is written by Microsoft, Google, Apple, or some open source folks. And this whole scheme breaks down if someone basically does a supply chain attack and introduces code there. So what you need is very similar to what you would have on the blockchain, which is you need a lot of people auditing software, making sure that they have an opinion on it, that it's crowdsourced, and then sharing that opinion. So think VirusTotal. When you upload a binary, right, there's always like 3 people that comment on every binary. I don't know who those 3 people are, but they managed to do it. And you have a bunch of objective viewpoints on that. The whole linchpin of confidential compute is that for CPU microcode, drivers, everything else that's loaded in these systems, that we also have public opinion on them. So that transparency ledger is super important, especially if you don't want anyone having access to your secret AI stuff. Apple does something interesting here too. You might have heard they're doing this thing called Apple Intelligence. They have basically invented a technology that's very similar. What they've said is on Apple Intelligence, we try to do things on devices for privacy, et cetera. When we can't, we will use like this OpenAI integration, et cetera. But that will be done on these Apple servers that have, guess what? A transparency ledger, attestation, and an active bug bounty program. So again, the objective of Apple here is to say, we're going to give access to top security researchers who will be able to look at this stuff. They would be able to tell you if you have any backdoors, and they're going to give you that information on immutable blockchain through this transparency ledger that makes things available, or blockchain-like protocol router. So in a nutshell, you can see there's a whole sea of different attacks and defenses that are required. You know, we say this every couple of years, there's really cutting edge technology. This time I really mean it. Like this is bleeding edge stuff. You can see even some of the best controls are not yet available on devices. So we're really in the midst of transformative. So the call to action I have for offensive practitioners is, I think you should start to look at how to augment your tradecraft with some of this AI. I called out, like, I'd be super surprised if Cobalt Strike doesn't get like search indexing, et cetera, with AI super fast. I'm not going to file a feature request, but I think that that would be relevant to help the general public understand the risks of these things. Hypervisor bypasses are becoming arguably the most important security bug out there. I think they'll just continue to become more relevant, so I think we need more offensive researchers looking at that. I think there'll be increasing attacks against UI. In this whole scheme, the one thing that's not protected is the UI projected back to the user. And that will become, I think, the point of weakness for attacks against this style of AI. So I think we need a lot more research into that. And then finally, what is the one area that's not fully protected in any of these models? That's active glitching or hardware attacks. Look, we've done well if we get to the point where we have to glitch a device to get access, but we should think forward to that. So I think there'll be a lot more research in that. And then finally, just to wrap up on the defense side, we need to make it fast and easy and available for CVMs for all developers to use. The stuff I've showed you today, no one's going to use unless it's super easy. So the job of the defense community, I think, is to build that. The second thing is we've got to make sure all GPUs and MPUs are confidential. I showed you like the top of the line, most expensive GPU for NVIDIA that does it. We need that to go down to like your average device. That's an important thing for defenders to work on. We can leverage this so-called software CVM until hardware is available. That gives us a lot of the protection. We need more engagement and thought into how these confidential ledgers work. What are the right protocols? What are the engagement of the security community? And then finally, we've got to think long and hard about how to make UI more secure, because this is the one piece of software attack surface that's not really thought through here. And with that, it's been a pleasure. Thanks, everyone. This is something that is super hot off the presses, so I hope you learned something, and I'll be around if anyone wants to chat. So thanks for listening.